All right, students, we have a problem here where we are going to do a calculation, a dilution problem. In the simulation itself, you'll be asked in the lab to do both sulfuric acid and hydrochloric acid. Today, we're going to be using phosphoric acid, which has the formula H3PO4. Now, I should tell you that in addition to H3PO4, there are a couple of other species that are kind of reduced versions of this. There's an H2PO4 and just an HPO4. They make up a very small portion, but they're there. And so you'll need to look carefully when we look at the molarity in the simulation for the phosphoric acid, because it will not be immediately obvious that the molarity is 14.6 unless you include the contribution of all the species that are present besides H3PO4. In any case, our stock solution for the model will be 14.6 molarity. And what we want to make is we want to make 365 milliliters of a dilute solution, which is only 2 molarity. Now, our formula says that the molarity of the stock times the volume of the stock equals the molarity of the dilute times the volume of the dilute, and that will give us the moles of solute. Why does that give us moles? Because molarity is moles per liter, and the volume is just liters. So when we multiply them by one another, the liters will cancel out. Now, it is a fact, however, that it is easier to measure in milliliters than in liters, but the unit of molarity, that concentration, is moles per liter. So if you're given some number in milliliters, you must first convert it into liters. Let me model that for you. In this case, 365 milliliters. This is the desired amount for our dilute solution. And so we'll use the fact that for every liter of solution, we have 1,000 milliliters. The milliliters, of course, will cancel out. And so this will become 0.365 liters. That's the volume of the dilute solution in liters. Now we're going to take our desired molarity, which is 2.0, and we're just going to multiply that, okay? So when we say molarity, what do we mean? We mean 2 moles per 1 liter. So that's our given concentration, moles per liter. And our volume is converted into liters. That's just 0.365 liters over 1. The liters cancel. When we do the math, we determine that we need, well, or what we're getting, we're going to have this many moles of solute. In this case, the solute is phosphoric acid. Okay. So we now know that the product of the molarity and the volume of the dilute solution is that many moles, 0.73, but it's also the same, 0.73 is also the product of the molarity and the volume of our stock solution. And we know the molarity of the stock solution. What we now do is we just simply take that 0.73 moles and we are going to multiply it by the molarity, where the 1 liter is on the top and our 14.6 moles is on the bottom. Because again, when we say 14.6 molarity, we just mean moles per liter, but in this case, we're just taking that conversion factor, moles per liter, and we're flipping it. And so we do it like that. And when we get done doing the math, what we're going to discover is that this is approximately 0.05 liters. Now, of course, at the end, it's more convenient to measure in milliliters. So once again, we're going to take the liters, we'll convert them back into milliliters, and we'll just use the same conversion factor, only instead of liters per 1,000 milliliters, the 1,000 milliliters will now be on the top, like so. And again, the liters will cancel, and it turns out we'll have 50 milliliters. That's the volume of the stock solution that we need. So the molarity times this number in liters equals the molarity here times that number in liters. So basically that's what we need of that. And since we need 365 milliliters total, the difference between the 50 milliliters of the stock solution and the total volume that we need in milliliters is 315 milliliters. So this is the prediction of the stock, and this is the prediction of the water, and when we add them together, they should be 365 milliliters. Okay, so we're going to take that math out for a test spin. We'll test it with the simulation right now. All right, we've calculated what we need. So now we're going to go to the Chem Collective dilution simulation. And we are going to go to our stock room, and we're going to get the stock solution of the phosphoric acid, which again is 14.6 molarity. We click on it, you'll see that that 14.6 is the sum of actually two separate ions, but when it says 14.274, there's some other ions present, but the overall molarity is 14.6. Going back to our stock room, we're going to also want to get the distilled water, and we need to be able to put in a total of 365 milliliters, so we also need a piece of glassware that can handle that. So I'm going to go and I'm going to get the 500 milliliter volumetric flask. Okay, so now we have what we need. We're going to start with our phosphoric acid, and again, we predict that we need 50 mils of this. So I position it like so. You notice it's set to precise, so we don't have to actually turn it on and off. And we've done that, and lo and behold, now if we click on our volumetric flask, it has exactly the same molarities for its dissolved substances as the stock solution, because, you know, it is stock solution. Now, we calculated that we needed a total of 365 milliliters, and we just put in 50 milliliters of the stock solution. So the difference between 365 and 50 is 315. So we need to put 315 milliliters of distilled water in the flask. So we're going to do that right now. Again, we're going to say precise. We pour, and so we have some pieces of data right now. We click on our volumetric flask. We see that we have exactly 365 milliliters, and we now have a different concentration. It's actually hard to see what that concentration is because it should be 2 molarity. However, if you look carefully, H3PO4 is 1.88, H2PO4 is 0.11, and then we have a tiny little business amount. So this is, in fact, approximately 2 molarity. Not obvious that that's the case, but that is the case. Okay, so if we get a result that's very similar to this, where these various species of ions, based upon hydrogen and phosphate, they add up approximately to 2.0. If you have some result that looks like this, you're very, very close. It's going to be, you're going to get a full credit for it. Okay, so make sure that you use the simulation to test your predictions, as I did, and you'll want to take a screenshot of that and include that as part of your submission. And I hope that was helpful.